Welcome to the Microservices Patterns and Practices track. I am your track host, Randy Shoup. All day, if you want to stay, are great lessons from people actually practicing microservices. Very little theory, lots of practical advice, so it should be pretty good. So I'd like to introduce the first speaker, who's the VP of Engineering at Stitch Fix. Hi, I'm Randy Shoup. I'm the VP of Engineering at Stitch Fix. I'm going to talk about microservices, in particular managing data in microservices. So here we go. Great, so I'd like to start with a little bit of background so that you kind of know where I'm coming from and know where some of these lessons derive from. So right now I'm VP of Engineering at Stitch Fix in San Francisco. We are a clothing retailer and we combine both art and science to give people the clothes that they love. I'm going to talk a little bit more about our business model and approach simply because it motivates the need for data and our use of microservices in a little bit. Before that, for about a year and a half, I was sort of a roving CTO as a service, as my friends used to say. I helped a bunch of startups in the Bay Area, larger companies in Europe and Asia, sort through their engineering organizations and try to figure out how to scale their technology. Earlier in my career, I was director of engineering at Google for Google App Engine. So that's Google's platform as a service, like Heroku or some other platforms you might be familiar with. And then earlier, I was chief engineer at eBay for about 6.5 years, where I worked on multiple generations of eBay's search engine. So very briefly about Stitch Fix. And I'm not trying to tell you you should buy your clothes from us, but you should totally buy your clothes from us. But I will tell you our model because it is very data-driven. So the model of Stitch Fix is kind of the reverse of a standard clothing retailer. So rather than going into a physical store or into an online shop and choosing your own clothes, let's have an expert do it for you. So you fill out what we call a style profile. It's about 100 questions, very detailed information about the styles you like, your price preferences, things you'd wear and don't wear, your age, your parental status, your occupation, everything that somebody would want to know to be able to choose the best clothes that you might enjoy. You're going to get in the mail 5 hand-picked items, so actually chosen for you by a human. You keep what you want and you return what you don't. In service of this, we combine art and science, in particular the data science part of science. So I believe this is unique in our industry, but we actually have a 1-to-1 ratio, essentially, between engineering and data science. So we have close to 100 software engineers that work on the team that I'm on. We have also close to 100 data scientists and algorithm developers, most of whom have PhDs in things like astrophysics and biochemistry and experimental psychology. And again, like I say, I'm very happy to be sort of proven wrong and hear the counterexample. But as far as I'm aware, certainly at our scale, there are no other companies in our industry that have this ratio. So what do we do with all those data scientists, right? I mean, they literally have developed exoplanets and now they're trying to choose clothing. So what do we do with them? We apply intelligence to every aspect of Stitch Fix's business. And just like any physical business, there's a whole supply chain. So we apply it to the buying area. What inventory should we buy, in what quantities, when should we have them arrive? We apply it to inventory management. So where should we ship, where should we store it? How do we pick things out of the inventory and get those 5 things in the box to you? We think about it in terms of logistics optimization. What's the cheapest and fastest way of getting our stuff from one of our warehouses to your doorstep? And I will motivate this example a little bit more, but styling recommendations, so algorithmic personalized recommendations for you as a client based on the millions of other customers that we have. And then we also do more standard things like demand prediction, because we have a physical business, so if we guess over or under on how many boxes we're going to send, how many clients we have, that's a real problem, right? So there are lots of virtual businesses where 2x more than you expect is a great thing. For us, that would be a disaster because it would mean that half of our customers wouldn't be able to be served. Does it make sense? Great. Okay. All of these things are about humans and machines augmenting one another, making each other better. So the humans are great, the machines are great, they are better together. I'm going to talk a little bit in detail about the styling part. So we say styling, that's the humans choosing the 5 items that go in the box. So we have 3,500 human stylists all around the United States that we use to help our clients, send our clients things we're going to like. So from the client perspective, Obviously, you know Stitch Fix has a bunch of inventory, and then magically, 5 items in a box show up, and hopefully you like them all. There's a little more to it than that. So breaking down that arrow, there's a first phase of personalized algorithmic recommendations. So this is what we're doing with a bunch of those data scientists. We look at our inventory, we do a ton of machine learned models, come up with a sort of ensemble score that predicts the likelihood that this particular client is going to keep this particular piece of inventory, and we produce those scores in a set of algorithmic recommendations. We then show those algorithmic recommendations to one of those 3,500 human stylists, and those human experts essentially curate the 5 items that are going to go in the box. So the machines are really good at going through all the data and coming up with those scores. The humans are good at putting together an outfit, answering client requests like, I need something sexy for date night with my husband. So far, we don't have a machine that knows how to interpret that, but maybe someday. That type of thing. The humans do what the humans are good at, which is the pattern matching and understanding context, and the machines do what the machines are good at, which is trolling through tons of data and making scores. Does this make sense? Right. And again, just like in chess, by the way, the humans are great by themselves, the machines are great by themselves, but they're even better when combined together. So how do we work at Stitch Fix, and why does it work? And I honestly, I promise you I will talk about microservices, but just in a moment. So modern software development, to my mind, that we practice at Stitch Fix and at Google, where I used to work, combines not just technology, but organization, processes and practices, and culture in addition to technology. And so what I'm going to do is I'm going to set up those first 3 really quickly, because they're kind of the background or the foundation on which we're going to build the microservices approach, and then I will leap into joins and transactions and all the sexy stuff. So, but in particular, just to telegraph where my beliefs, I believe that organizations are most effective when we build them out of small teams with well-defined areas of responsibility. Processes and practices, I believe those are best practiced with test-driven development and continuous delivery. For culture, I believe strongly in DevOps in the sense that you build it, you run it. And for technology, at least at our scale, I strongly believe in microservices. So again, first, talk about those first 3 very quickly to give the kind of background and sort of the underpinnings or the prerequisites for being successful with microservices, and then we'll go and talk about the technology part. So first, I want to talk about small teams. We practice at Stitch Fix, and we also used to practice at Google, this idea of small service teams. So we have small teams that are directly aligned with a particular domain in the business. Those teams have a clear, well-defined area of responsibility, and they typically build and maintain a single service or application or a set of related services and applications. Those teams are cross-functional, so within the team boundary, they have all the skill sets that they need to do the job. That doesn't mean they have all skill sets in life. We don't build our own hardware, we don't write our own operating system, so we don't have those folks. But all the skill sets that are needed to produce the particular service are within that team boundary. And of course, teams depend on each other, right? So we depend on other teams within Stitch Fix. We also depend on external third parties, cloud providers, et cetera, for supporting services and libraries and tools. Does this make sense? Great. Okay. This is a brief tour. So next I want to talk about our practices around test-driven development and continuous delivery. So for test-driven development, we don't do this to slow things down. We do this to speed ourselves up, right? Tests help us go faster. Why? Because tests have my back. When I am writing code, or more precisely, when I am changing code, the tests make sure that I don't regress the things that already work. And it actually increases our development velocity by making that investment up front in writing the tests rather than writing the code, hoping it's going to work, and then kind of testing manually or not at all at the end of the process. Tests make better code. So when I have a large suite of automated tests, it gives me the confidence to break things, and it gives me the courage to sort of mercilessly refactor areas of the code, change cross-cutting concerns all across the code base, exactly because I know if I make a mistake or I don't do things properly in one area, the tests are gonna catch it. Does it make sense? Tests make better systems. Obviously, having automated tests allows us to catch bugs earlier, and it allows us to fail faster when it's a lot cheaper in the development cycle, rather than finding out only much later when we ship stuff to customers that the thing doesn't work. So I've been in the industry a long time, as you can imagine by looking at me. Often I hear this. Has anybody else heard this? We don't have time to do it right. Yeah, maybe half of the people. So here's what I say. Do you have time to do it twice? That is the choice. You can do it right the first time for some value of right, or you can do it twice. That's it. Or it doesn't matter, right? I guess the step 0 is, does the thing we're doing actually matter? In which case, it doesn't matter whether you do it right or wrong. But if it matters, do it properly so you don't have to do it again. Do it right enough the first time. And in fact, this is a bit counterintuitive, but stay with me. The more constrained you are in time and resources, the more important it is to build this thing solidly. Does it make sense? When I don't have a lot of time to come around and do it a second time, let's make sure that I do one thing really well and then I move on, right? I would much rather, as a startup or a medium-sized company or a massive enterprise, I would much rather build one great thing than 2 half-finished things, right? Okay. Right doesn't mean perfect. So there's an 80-20 rule, Pareto principle here. Obviously, with the idea is that with 20% of the effort, we can get 80% of the way there. So what I am not suggesting is build a perfect system, but I'm saying build a just right enough system to get you going, move on, go to the next thing. The interesting implication that has at Stitch Fix is basically we don't have a global bug tracking system. Now, I don't say we don't have bugs. We have lots of them. But for the most part, when we find a bug, we just fix it, right? We find some issue, we write a test that demonstrates the bug, we make the fix, the test verifies the fix, all done, closed, move on to the next thing. Do we have lots of other things we want to do? Of course we do. We have a large backlog of stuff to do. But that backlog is not a list of half-implemented things. It's not a list of things that we thought were working and aren't. It is a list of new things that we want to do, right? New features that we want to produce, technical debt, which we absolutely have, technical debt that we want to repay. But what it isn't is a list of, the endless list of priority 2, priority 3, priority 4 issues that we know we're never going to fix. And this, for me, is unique in my entire 27-year experience in this industry. I've never worked at a place that had this. And this is exactly and directly comes from the test-driven development approach. Does this make sense? Does it sound pretty cool? Yeah, it is. Okay, continuous delivery. We build stuff on Ruby on Rails for the most part. Rails really wants you to build a monolith, and we really didn't. So thankfully, we avoided that siren song. We've ended up building about 50 or 60 different individual applications and services, most of which are deployed multiple times a day. By having the ability to deliver continuously, we build more solid systems. Why? Because we release smaller units of work into smaller batch sizes, to use the lean terminology. It means we have smaller changes to roll forward or roll back. And if there's an issue, it's faster to repair, it's a lot easier to grok, it's a lot easier to understand, and it's simpler to diagnose. Does this make sense? Yeah. It also allows us, as we will see going forward, to rapidly experiment, right? Our ability to release small units of code multiple times a day allows us to make rapid changes to the code, rapid experimentation, which we absolutely on the data science side take advantage of. So we experiment, constantly, and we rapidly iterate exactly because we've made it cheap for ourselves. Okay, last thing I want to talk about is the cultural aspect of DevOps. So apparently there are lots of definitions of DevOps. Here's mine. It means end-to-end ownership of the thing that you are writing. So unlike when I started in the software industry and we built shrink-wrapped software that we put on a CD and we shipped physically to customers, our teams in the modern world, when you're building sort of an online system like Stitch Fix is, the team is going to own the service all the way from the design through the development, deployment, all the way to retirement. So when I started, my job was done when I sort of hit commit and my thing went into the repository. Now I am only done when the service that I'm working on is retired. At Stitch Fix, we just have engineers. And this is very similar to Netflix, to Google, to Amazon, lots of places that are really high performing. Those engineers that I have on my teams are responsible for all aspects of the software development process. They are responsible for the features. They are responsible for the quality of the features. They are responsible for the things that they build performing well. They are responsible for operating them, and they are responsible for maintaining them long term. So we do not have a separate QA team, a separate performance team, a separate operations team, a separate maintenance group. We have engineers, they do it all. And that has wonderful properties because it means that the things that we learn operating and maintaining the software feed directly back into the software that we're building. It's basically a reification of the Werner Vogel's idea of you build it, you run it. Does this make sense? Okay, so all of this is backstory to getting to where you really wanted to hear about, which is microservices. So that's what we're going to talk about for the rest of the session. First, I will talk a little bit, I will show a little bit about the evolution of companies you've heard of to microservices. So very briefly, eBay is what you would currently characterize as a microservices architecture, completely didn't start that way. So it's depending on how you count on it, about its 5th generation of its architecture. So a 5th complete rewrite from the ground up. So it famously started in 1995 when Pierre Omidyar, the founder, took a 3-day Labor Day weekend and started playing around with this new thing called the web. And he decided to build an auction website. Took him 3 days. It was monolithic Perl application. Every item was an individual file on his machine. That didn't scale, but it was pretty cool. The next generation was a monolithic C++ application, which at its worst was 3.4 million lines of code in a single DLL. Don't do that. You think you have a monolith? I laugh. That's a monolith. They were actually hitting compiler limits on the number of methods per class, which is 16K. Yeah. Next generation, the V3 was a rewrite in Java. That wouldn't fairly be characterized as microservices, but maybe mini applications, right? So individual pages of the site were served by, the search application or the selling application or the buying application, something like that. And now I think it's fair to characterize eBay as a polyglot set of microservices. Twitter's gone through a similar evolution. They're about on their 3rd generation. So they started famously as a monolithic Rails app, which the Twitter people called the monorail. Very clever. Next generation of it was sort of breaking out more of the front end into JavaScript, more of the back end into services, mostly written in Scala. And then now I think it's fair to characterize Twitter as a polyglot set of microservices. Amazon has gone through a similar evolution. Amazon isn't so clean on their architecture generations, but it started out as a monolithic Perl and C++ application, which actually you can still see the history of in some of the product detail pages. So if you ever see in the URL Obidos, O-B-I-D-O-S, that was the name of the original monolithic app in Amazon. The next generation after that was breaking out a bunch of back-end stuff into services, mostly written in Java and Scala. And then now it's fair to characterize Amazon as a polyglot set of microservices. So there are 2 things to take away from this, which is why I showed this slide. Number 1, no place you've ever heard of started with microservices. And number 2, no place at this scale has not ended up in microservices. Does it make sense what I'm saying? Yeah. Okay. So I want to super underline this because I'm going to talk about microservices, but I want to make sure that microservices are not for every company and are particularly not for every stage of company. When you are at eBay scale or Google scale or Netflix scale, you for sure need to have something that looks like microservices. When you are a tiny startup, it is unclear that that is the right way to go. So I love the Martin Fowler thing where, the first law of distributed object design is don't distribute your objects, right? A monolith is perfect for when you can get away with it. At some point, you will no longer be able to, but it's great to start with. We did that at Stitch Fix, same at Netflix, same at all these other places. There's no shame in that, and there's everything right about starting in a monolithic approach. So this is what Martin Fowler says. This is what I say. If you don't end up regretting your early technology decisions, you probably over-engineered, right? There might well have been an eBay competitor in 1995 that spent all their time building a distributed system. There is a reason why we have not heard of that company. All right, microservices. My definition, it's not about how many lines of code or how long it takes to write them. It is about the scope of the interface. Microservices are single purpose. They have a simple, well-defined interface. And the critical aspect from an architectural perspective is that they are modular and independent. Now, if these things sound like you could get them in other ways without microservices, you would absolutely be right. In fact, as I like to say, microservices are nothing more than service-oriented architecture done properly, right? It is a service-oriented architecture where we actually think about bounding the context of the individual services. We think about doing one thing, doing it very well, and then moving on to another service. But another thing which is going to motivate some of the data stuff that I'm going to talk about going forward is, in order for microservices to be really effective, they really have to have what I call isolated persistence. And I am going to talk about this in much more detail, but the brief overview here is that an individual microservice in one of those ecosystems really needs to have its own isolated database, essentially. There should not be any backdoor way for microservices to kind of sneak in and look at the other guy's data. That's not going to work, and I'll tell you why. Okay, so I'll tell you why now. So let's talk a little bit about some options for how you can get what I just said. How can you make microservices sort of have isolated persistence from each other? So the first approach is that the same team that builds the microservice also operates its own data store, right? So we use Postgres at Stitch Fix. You might choose your own data store, whether it's MySQL or Oracle or Cassandra or something like that. So the idea is that the team would store to their own instances and sort of own and operate those databases. And we absolutely do, in some teams at Stitch Fix, we absolutely do this model. The other model, of course, is to use a persistent service, whether that service is provided by potentially another team in your company or maybe a third-party cloud provider or something like that. So the idea there is you store to your own little slice. You store to your own schema in, I don't know, Amazon Dynamo or Google Cloud Data Store or Google Spanner or Microsoft SQL Server in the cloud, something like that. But it's the idea is that it's operated as a service for you by somebody else. And the key thing is that even though there might be a kind of multi-tenant situation, you are isolated from all the other tenants, right? All the other users of that service. So you have your own little slice that, as far as you're aware, is alone. Is this making sense? Yeah. The key thing to get here, though, is that the only external access to your data store in your microservice is through your publish service interface, right? If you have any other way of getting there, that way lies madness. You really don't want to have people reading and writing behind your back without your ability to execute business logic and all that. And eBay absolutely did do that in their first attempt to do services, and it was a massive failure exactly because the applications could talk to the shared databases directly and didn't need to go through the service layer, so nobody used it. So don't do that. That's why I'm telling you this. Okay. Next thing I want to talk about, and these are all kind of architectural building blocks that we're going to build up to talking about joins and talking about transactions near the end. So I want to take a brief pause and make a pitch for having events as a first-class construct in your design and in your architecture. So Wikipedia defines an event as a significant change in state. I like to think of it as it's a statement that a thing happened, like something that something that I cared about happened in my system. Typically, these things are asynchronous, so there might be nobody listening to the events that I produce, there might be one other consumer, or there might be many other consumers for the events that I produce. In a traditional, we're all pretty familiar with the traditional three-tier architecture. A lot of us, myself included, sort of cut our teeth on building systems like that. So there's a presentation tier, a sort of application or business logic tier, and maybe a persistence tier, which is often, at least traditionally, a relational database. I think we are missing something. I think we are missing the fourth fundamental building block of architecture, which is state changes or events. Hopefully I will motivate this in the next slide. But I think not thinking about events as a first-class part of your architecture, you're missing a whole dimension of architectural flexibility that you have. Okay, why should you do it this way? Well, it turns out that events represent how the real world actually works. In finance, Deutsche Bank and Bank of America, when they're trading currencies, they don't do a distributed transaction. They are firing events at each other, and then at the end of the trading day, they kind of reconcile, right? I've sent you 1 million events, you've received, 1,010,000 or whatever. We figure it out at the end of the day and reconcile. I was looking for another example that's sort of more visceral for people in this room. Think about it as the software development process itself. So raise your hand if when you hit return in your IDE that it gets deployed to production. Anyone? Yeah, one person, great. I'm all for continuous delivery, but I strongly believe that there are steps along the way, and it's actually a workflow with, I finish building my code, locally, and then I commit it to the repository, and then, CI happens, and then it gets deployed, et cetera, et cetera. So they're actually events and a whole big chain. Great. So now I want to talk about events as applied to microservices. So just like it should be a first-class part of our architecture, events are a first-class part of our service interface. So the obvious part of my service interface as a microservice is the synchronous part, right? So often that is, REST and JSON, or maybe it's something like gRPC or Thrift. But typically people think of their interface as that synchronous request response part in the front. Well, there are lots of other parts of our interface as well if we kind of open our eyes. So the interface to my service also includes all the events my service produces, right? It includes all the events my service consumes. And also, as is often true when I'm communicating with analytics systems, it also includes any bulk reads and writes, like ETL jobs, to my database. Does this make sense? Great, lots of nods. Okay. The interface includes any mechanism that gets data into or out of my service. Okay, which includes events. All right. Now that we have all those building blocks, I'm going to talk first about how to extract microservices from a monolithic database. Then I'm going to talk about some techniques for managing data from the design perspective in a microservices ecosystem. So this is exactly the problem at Stitch Fix when I joined, and we're still working through it. So Stitch Fix, as I mentioned, avoided the siren song of building the Rails monolith, but we did, I think for very good reason, we did build a monolithic database. So almost even now, even though we've been at it for a while, almost every interesting entity in Stitch Fix lives in this shared database, right? So all the information about clients, the information about the shipments we've sent out, the items that we have in inventory, all the metadata about items, so styles and SKUs, all the information about our warehouses, et cetera, et cetera, et cetera, times 175 tables. And we have a bunch of applications. I show 8 up here, but we actually have about 50 or 60. And the vast majority of them are still talking to this shared database. So this is a real problem, right? It's a single point of sort of contention and restriction on feature velocity for my teams, but it is also a single point of failure, right? So if this thing goes down or is slow, all of Stitch Fix has a bad day. So let's make sure that doesn't happen anymore, and I will tell you how we are doing it. So the solution is decoupling applications and services from the shared database. So that's pretty obvious. I'm going to tell how we do that. But I'm going to tell it in a slightly simplified form just so that there aren't so many boxes and lines on the slides. So let's imagine we only had 2 applications and we had 3 tables. So step 1 is we're going to create a service for one of those shared tables. So we have a service at Stitch Fix which we call Core Client. As you can imagine, it stores information about our clients. So we create a client service. Now instead of having the applications talk directly to that database table, we change the applications to talk to the service instead. This table is still in the shared database, but it is all the interactions with that table come through the service interface rather than going directly against the table. The next step is to move that table out of the shared database into a private or local database owned by that service. And then we say rinse and repeat, right? So we do that for the next thing. So we create an item service and we move the core item table out of the shared database into a private database owned by that service. And we do the same thing with SKUs or the metadata about our inventory. So we create a style service and that manages SKUs. Does this kind of make sense what I'm saying? Does it seem super overly simplistic? Yes. It is, except I've never seen any one of these extractions work any way other than this. If you want to break up a monolithic application, there are other techniques, but breaking up a monolithic database, this is the way to do it. It seems even to me, even though this is probably the 20th time I've said this in front of an audience, it still seems overly simplistic. So what it elides is not that there are missing steps, it's that each step is actually pretty complicated. Does it make sense what I'm saying? Creating that service, like there's a lot of negotiation and discussion about what that service interface should be. Changing the code just is a little bit more than just pointing 2 lines from the table into, into some other place, because there are lots of joins to unroll and lots of other dependencies to manage. But that is the next step, having everything go through the service interface, and only then can you remove, that table from the shared database and put it somewhere else. Anyway, so as I mentioned, this whole track is about patterns and practices and people actually doing it. We are actually in the process of doing all this at Stitch Fix right now. Okay, and so here are the service boundaries, right? And I very intentionally draw the boundaries around both the application part, or the sort of business logic-y part of the service, and the database, because nobody should be able to get into one of these bubbles except by going through the published service interface. Make sense? All right. Now we have started extracting things into microservices. Let's talk about some of the techniques around managing data in this environment. And I'm going to talk about 3 of them. I'm going to talk about shared data, I'm going to talk about joins, and I'm going to talk about transactions. All of these things are wonderfully, trivially easy and powerful within a monolithic environment, and they are all made more challenging in a microservices environment. So just as we have, discovered and rediscovered these techniques, I want to share them with you so you don't have to rediscover them from whole cloth, as maybe we did. Okay, so the first one I want to talk about is shared data. The problem here is simply stated. In a monolithic database, it's very easy to leverage shared data. So there's some table in there that represents, I don't know, some metadata or something that's shared. I can just join to it, right? The customer table is right there. I need customer information. I can go right in there. Just add it to my from clause and I'm good. And that works fine in a monolithic environment. That does not work at all in a microservices environment where each thing is behind a service interface. So how do we do it? There's a real problem here, and we can't define the problem away, so how do we do it? 3 techniques that I want to talk about. Before I do that, there's a principle here, which is that every interesting piece of data that we have should be owned by a single service. So there is one place in the overall infrastructure of Stitch Fix, or Google, or Amazon, or Netflix, where that owns a particular piece of data. There is one service that owns the customer. Customer information is also often used by lots of other places, and sometimes even cached. So every other copy, in this example, of customer data in our infrastructure is a read-only, non-authoritative cache. I'm going to let that sink in a little bit. Does this make sense? There is one place that owns reading and writing this thing. Every other place that understands anything about customers, the address in the billing information in the billing service, all that stuff is just a read-only, non-authoritative cache of information that is actually owned by the customer service. And this principle is going to help us as we figure out what to do about when we make changes to customers and what does that do with caches and so on. This kind of making more sense? Nods? Okay, nods and photographs. Okay, cool. So this is the problem statement and the principle for the solution. So approach 1 is just synchronously look it up from the place that owns it, right? So in this particular example, the customer service is going to be the thing that owns customer data. Let's imagine we have a fulfillment service which is going to ship things to customers. That fulfillment service needs to know the address where the customer, lives or wants us to ship a thing. So one totally legitimate way to do it is the fulfillment service in real time calls the customer service and says, what is this person's address? This make sense? Pretty simple. Okay, the second second option is, let's imagine that for whatever reason it's too expensive for the fulfillment service to ask the customer service in real time. Instead, the fulfillment service will maybe maintain a cache of the customer data that it cares about. So again, in this example, the customer service is the canonical system of record for the customer data. The customer service produces an event that says, address updated or something like that. The fulfillment service listens to that event and then updates its local cache. Does this make sense? Cool. All right. There's a third approach, which is for things that are shared metadata that don't change very often. So examples in Stitch Fix are things like size schemas. So that's like for women's sizes, 2, 4, 6, 8. small, medium, large, extra large. So like one could certainly imagine creating an extra, 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 extra large, and maybe if current trends continue, we might have that in the United States. But that doesn't happen very often. Similar things, at least in our domain, are things like colors, fabrics, the US states. So I hope nobody has a US state service that says, you know, what are the US states? And it returns the 50 US states. Like, it's been the same for 60 years. And maybe someday, you know, Puerto Rico will become a state. That would be awesome. But, you know, until then, that doesn't change very often. So here's how we do it. And I use, you know, we do Ruby on Rails for the most part for our applications at Stitch Fix, in addition to a bunch of backend services in Go. So I use the Ruby icons here just to show that. So let's imagine that we have one of these pieces of shared metadata, and we just distribute, you know, the color schemas to all these different places. Does this make sense? So shared library is a totally legitimate thing to do, even though we also have services in our toolbox. And I guess the meta point with all these things is there are lots of different ways to do it, and just because we're in a service world or a microservice world doesn't mean that we have to forget about other techniques that we've been using for many years to solve problems that are like this. Okay, so that is shared data. Now I want to talk a little bit about joins. So again, the problem statement. In a monolithic database, joins are super easy. That's one of the most wonderful things about having a monolith. If I need customer data, I just join to it, and there it is, and it's in there and great. Once I have split my data over multiple services, this kind of stuff isn't as easy anymore. But I still want to be able to combine, you know, customer data with order data or something like that. So the problem is still there. I just need to solve it in a slightly different way. So I'll give a couple of techniques for that. So approach one, again, this is pretty obvious. Approach one is simply joining in real time in the client application, right? So let's imagine we have an order history page. So we want to show to one of our customers, here are all the orders, you know, that we sent to you. So one could certainly imagine that order history page going to the customer service and saying, get me the information about this customer, and then separately going off to the order service, you know, in parallel or in serial or whatever, going off to the order service and asking for all the matching orders for that customer. Does this make sense? Yeah. If this doesn't seem familiar, it's, oh, sorry, and this use case, this approach is best when it's a kind of one-to-n join, right? So there's one customer with many orders. If this seems familiar, it's every web application you've ever built. unless every aspect of your web page comes from one and only one data source, every web page is like this. I go one place for the customer data, another place for the order data, and we put it all together and we show it as one thing. Okay, that is one very legitimate approach which we absolutely use at Stitch Fix. Another approach which we also use is an approach that I call materializing the view. So the idea here is that it might be that I can't join in real time because there are lots of items and lots of pieces of feedback altogether. Like maybe there's just too many items and too many other things on the other side of the join, and it's just too expensive to join in real time. So what I want to do is essentially maintain a cache of that join wherever I'm using it. So how does this work in practice? Let's imagine that there is, whoops, there we go. Let's imagine that there is an item feedback service where we want to show all the feedback that our customers have given about each item. So we have a bunch of individual items and lots of pieces of feedback about each item. So it's a many-to-many relationship or an M-to-N join. So this item feedback service might maintain a denormalized cache of items joined to order feedback by listening to events from the item service, and then separately listening to events from the order feedback service, and then updating that join in real time. Does it make sense? Yeah, so I'm using database terminology here very advisedly. So this is in Oracle or SQL Server or some other, you know, commercial grade relational databases, there is an idea of materializing a view. This is a join, and you just simply maintain a cache of it, and it gets updated by when the individual kind of elements of the join get changed. Okay, if this seems a little bit weird or unfamiliar, let me give you some other examples of that common systems that you use every day that do this. Almost every NoSQL approach takes this tactic. Relational databases optimize for the write side. You write individual records, and then at the read time, you combine them all together. Most NoSQL approaches, the Cassandras, the Reacts of the world, are mostly the other way, where instead of writing individual things and joining at the end, you write in parallel a bunch of different, you basically write all the queries you're going to ask in parallel, and then you ask the queries, and the queries are fast. Again, as I mentioned, lots of commercial-grade database systems have this concept of a materialized view. Search engines are like this, right? So if you have an Elasticsearch in your, anywhere in your infrastructure, probably you are doing a thing just like I mentioned. Every analytic system in the world is combining together, joining together data that comes from multiple data sources, and also log aggregators for operational logs. So lots of use cases for this particular pattern. Does this make sense? Okay, we're going to step it up a notch. Now we're going to talk about transactions. The problem here, or the wonderfulness in the monolithic database, is that transactions are super easy, right? I want to update atomically A thing and B thing and C thing and D thing in one unit. I want it to be ACID, all done or not done at all. That is really easy in a monolithic database, and it is very hard to cross services. What I do not recommend is thinking about it as a like a distributed transaction, two-phase commit. Please do not do that. That's a scalability killer and a performance killer. But I will give you some techniques to get most of what you want from the transactional world. Okay, instead of thinking about it as an atomic transaction, think about it as what's called a saga. People have heard the term saga? It's okay if you haven't. Wow, more than I expected, maybe a quarter of the people. Great. Katie McCaffrey from Twitter, who just left Twitter, has given a wonderful set of talks specifically about sagas, way more detail than I can give you in 2 seconds. So that's worth taking a look at if this is unfamiliar. But the general idea is take that transaction where I wanted to update A and B and C and D together, and think about it as a workflow. Think about it as a state machine of first I update A, then I produce an event and update B, then I produce an event and update C, and then I produce an event and update D. So think about it again. Think about it as a saga or a workflow of individual atomic transactions that are each within a service boundary, but you connect them together with events and you maintain a kind of state machine of where you are. Is this kind of somewhat making sense? Yeah. So how do you do rollback, Randy? I'm glad you asked. You just run the workflow back the other direction. So you apply what are called compensating operations that undo the thing that you had done in the forward direction. So let's imagine we got all the way to updating A and B and C and D, and then we needed to roll back for some reason. You would remove the thing that you added to D, or sort of undo that update. It would produce some events. It would update the C, it would update the B, and then it would update the A. So just in the same way as, you know, there's a forward movement through your state machine in the commit case, there is a backward movement through your state machine in the rollback case. Making sense? Yeah. If this does not seem familiar, let me give you some ideas where this happens all the time. Every single payment processing system that you could imagine works this way. Again, financial systems do not do distributed transactions for the most part. So anytime you interact with a third-party payment provider, like Visa or Braintree or something like that, they are going through a workflow. They first do this thing, and then they acquire the thing, and then they go to the bank, and I don't know this stuff, but they go to all the different banks and do all the individual sets of things, and at the end of which my money moves from my pocket into somebody else's pocket, something like that. Every approval workflow that you've ever seen in your company, expenses, first it goes to this person, and then it gets approved or sent up to the next person, et cetera. Randy, expense for the jazz club, goes up and gets rejected by the CEO, unfortunately, and back down. And then I try to, but the jazz club was for work. And yeah, that didn't actually happen, but I'd like it to. Yeah, so any multi-step workflow does this thing. Okay, so the last thing I want to say about transactions, because we do have a whole serverless track, which you should absolutely attend. I sort of feel like I can't, in fairness, end a microservices talk without giving a bit of a nod to the serverless techniques. I would prefer to call them functions as a service instead of serverless, but that's just me. Serverless is a great way of implementing what I just talked about. Why? Because the operations that I want to take in this workflow are super small, right? It's very lightweight logic. Maybe when you get right down to it, 10 or 20 lines of code. They are stateless, right? So I receive an event, I do some computation, and then I produce an event. And it's also, again, triggered by events. So something like Amazon Lambda or Google Cloud Functions or Azure Functions are a perfect match for this thing. Does it make sense? It is super small, targeted, stateless logic that is triggered from events and producing events. So serverless is a perfect technique for this. Okay. So just to sort of sum up, again, as I mentioned, I think to do microservices well and to develop software in a modern way, you want to have organizations that are sort of built out of small teams. You want to do practices of sort of test-driven development and continuous delivery. From a cultural perspective, you really want a culture of ownership where the same team that builds a thing also operates the thing. And then, again, at the kinds of scale that we're talking about here, the scale of team size scale and the sort of load scale or customer scale, web scale, microservices are a really great way to go. So I do want to make sure that I leave a few moments for questions, but I'll leave this up. I would be remiss in our modern world to not mention that Stitch Fix is hiring. And in particular, so we're based in San Francisco, but less than half of my engineers actually live there. More than half of the engineers at Stitch Fix are scattered all around the United States. Some in our regional offices in Austin and Pittsburgh, but also people from all over the country, all the way from Hawaii to New York and New Jersey, down to the Carolinas, like all over the place. And we're hiring in application development, which are the kinds of things that the customers see. We're hiring in our platform group that builds the underlying technologies that I'm talking about, and then we're hiring in that data science team that tells us how to be smart. So if any of this sounds interesting, I'm going to be around for the whole rest of the conference, so please see me in person physically or contact me virtually in one of these ways, because yeah, Stitch Fix is a great place to work, and if this stuff sounds cool, then come join us. So now I think I have a few minutes for questions. I can repeat it if you yell it.
So as far as I understand it, distributed systems are very good at exactly once. Very good at exactly once event delivery.
Yeah.
One of the questions that I've always had about the second shared data example is how do I deal with events never arrive or events twice?
Yeah, that's a very great question. So just to replay the whole question, distributed systems do not do exactly once delivery, true statement. How do you deal with events not arriving, coming out of order, coming due multiple times? Yeah, that's a whole talk in itself. I mean, I will give you an answer, and also it's a whole talk in itself, which hopefully I'll deliver at some point. So the first point, exactly once delivery, that is a myth. The FLP result shows that it's actually impossible in practice to get that. You can get maybe close in lots of situations, but you can't get, in the same way as you can't have perfect availability, you can't have exactly once delivery in all situations. So true statement, don't rely on that. Okay, what do you do? So that means that you might get events out of order, you might get events multiple times. Does it make sense? Okay, first step, so there are two ways to design an event system. One is called at least once delivery, and the other is called at most once delivery. You want the first part. So at most once means that you will receive an event either 0 times or 1 time. Only do that mechanism when you don't care about that thing, right? So actually logging is a great example. So there are lots of logging systems that use UDP or unreliable protocols exactly because if that logging message didn't get there, shrug, no big deal. But anytime you use events for business stuff, you want to use the at least once. So if there is a situation, if something goes wrong, or if the sender does not know that it was sent properly, then the sender will try to send again. So that is the at least once delivery. Okay, we'll start from that. So now with at least once, you have two problems. I will get the same thing multiple times, and I will get them out of order. At least the multiple times forces your consumer of the event to be what's called idempotent. So idempotency is a mathematical term. It means that f of x is the same as f of x. So for the non-math majors, I was a math major, for the non-math majors in the room, what that means is if I do a thing one time or I do it many times, I have the same result. Does it make sense? Idempotency. So you need to write your consumers in order to be idempotent. So if I do a thing, if I increment a counter, I need to make sure I don't increment it multiple times. There's lots of good academic work on techniques for doing that. They're a little complicated, and please don't try to discover them from first principles. But you should know that there are lots of techniques in our computer science toolbox for doing idempotent things no matter what you're trying to achieve. That is the idempotency part. For the events received out of order, if you care about the ordering of events, and first off, I would try to see if you can avoid caring about it, because oftentimes it doesn't matter what order they come in for lots of use cases. But when it does, then you will need to maintain some state on the server side, on the consumer side. Does it make sense? Like, let's imagine that I have events that say I create a customer and I delete a customer. Let's imagine that those come out of order. So I first get the delete customer, and then I get the and I get the create customer. Uh-oh. The end of which, if I didn't do it properly, then the end result of that is that I have a customer when what I intended was that I didn't. Did the example make sense to people? Nods. Yeah. So again, I'm going to get a little fancy. Look up CRDTs. They are data types. What is it? Concurrent replicated data types, something like that. Anyway, there are lots of sort of techniques in the literature about how to deal with all these things, and including the exact example that I gave there. There's a thing called tombstones, which is implemented in Cassandra and other distributed systems that have to deal with this, where like if I received a delete, I kind of remember the delete for a while, just in case somebody comes along with a create. Does it make sense-ish? Yeah. The thing you should take away is not that you know the answer, is that you know that there is an answer and you can go look it up. I am being told to get off the stage and give you an opportunity to get some more coffee. But again, I'm going to be around for the whole rest of the conference. Please enjoy it. And I hope you stay in microservices because we're going to have an awesome day. Thank you.